All right, in this lesson, we're going to be verifying trigonometric identities. This is chapter 6, section 2, and I broke that section into 2 days, so this is day 1. What does it mean to verify an identity? Well, when you kind of scan what we have here in front of us, we have equations, but our objective is to transform one side of the equation and make it look like the other. We're not going to assume that these equations are true until we prove that they are true. So verifying means take maybe the more complicated side of the equation, do some substitution, maybe some factoring, maybe some distribution, do different things on this side of the equation, which in example 1 is the more complicated side of the equation. Do some changes on this side, working down, and our goal is to get down to 1, what this is over here on this side of the equation. So for verifying identities, we don't assume that the equations are true. We want to prove that they're true. So starting with number 1, the product of secant y times cosine y is supposed to be equal to 1. Let's prove it. Well, some of the things that we can do is we can study what we have here. And when I think about looking at secant of y, I think about, well, maybe I should change that to its reciprocal by the reciprocal identity. So secant of y is actually equal to 1 divided by cosine of y. So I'm going to substitute in this reciprocal identity for secant of y. But I still have times the other factor right here, cosine of y. And because I just created a fraction from secant of y, I'm going to make cosine of y a fraction by putting it over 1. In our work, let's just go ahead and bring down equals and then bring down 1. You know, actually, I think what we'll do is we'll just bring down the equals. Our goal is to end up with a 1, but we're going to work down. Studying what we have here, we know when we multiply fractions, since cosine of y and cosine of y are the same things, they'll divide out and we're left with 1 over 1. So 1 is what we get from this side of the equation. We'll bring down what our target answer was supposed to be, which is 1, and we're done. It's a pretty basic little trig proof, if you will. There was only one step there. Of course, they're going to get more complicated, but hopefully we'll just kind of build up our skills to be able to handle the more complicated equations. All right, let's take a look at number 2. First thing is I kind of observed that maybe the left-hand side of the equation looks a little more complicated than the right-hand side of the equation. That's a good entry point into beginning to solve this problem. All right, there are going to be several ways perhaps to solve this, but one of the first things I think about here is when I work on this side of the equation, I'm looking at maybe changing tangent to its quotient property. So let me write a fraction bar down for the fraction bar that I have here. Let's keep sine squared of t on top, but when we focus on this part of the fraction, the denominator, I'm going to change tangent to sine over cosine. I have to keep the power with it, so it's sine squared t over cosine squared t. Then I'm going to think about keep, change, flip, or multiplying by the reciprocal. So if I multiply by the reciprocal, I still have the numerator. I keep the numerator, excuse me, and I'm going to multiply by the reciprocal of the denominator. Go ahead and make sine squared t a fraction. Put the equals here. Remember, this is our target. That's our answer we want to get by working on one side of the equation. The sine squared t's will divide out into a 1, and we're left with just cosine squared t. Here's your equals. Because we end up with the same thing we have here, we'll just draw a little arrow bringing down cosine squared t. So we're doing what we call trigonometric proofs, probably a lot easier than what you remember as far as geometric proofs. So trigonometric proofs just mean we're going to take an equation and prove that it's true. That's called verifying an identity. Let's look at number 3. All right, let me first figure out what I think is the more complicated side of this equation. Really, it's probably either side you could begin with. I'll just go ahead and work with the left-hand side of the equation. Some of the things to look for, some look-fors are you have powers going on here, and these powers are 2s. They're not 3s, they're not 4s, They're not exponents of 5, 6s. One of the things I think about when I'm having my formula sheet kind of handy is I think about the Pythagorean identities. You might remember that the Pythagorean identities, and here's your formula sheet, are right here. The Pythagorean identities have squares in them, not cubes, not to the 4th power, 5th power, etc. So one of the things to think about is, am I going to be using some Pythagorean identities because I do see the indicator of the squares? Maybe. Maybe I might use some of the tangent and cotangent identities. Maybe I'll use some of the reciprocal identities. So just have your formula sheet handy. One thing I notice is that if I'm going to transform the left side of the equation to the right, notice what's missing over here. I do not want to have a cotangent squared b, beta, which is present over here. So maybe that tells me I should work on changing cotangent squared b to something, beta to something. So let's go back to our formula sheet. Where is cotangent squared beta? Well, instead of beta, it's a u. I'm thinking I'm going to use this Pythagorean identity to help me get rid of cotangent squared of beta. Now on your formula sheet, I believe I had you at the bottom down here rewrite the Pythagorean identities in different forms. We just rearranged each of these Pythagorean identities 2 other ways. So right now I want to get cotangent squared beta by itself, so I'm going to subtract the 1 to the other side. So for cotangent squared beta, I'm going to replace it with cosecant squared beta minus 1. All of this came from replacing cotangent squared beta. Go back to the left-hand side of the equation and bring down the rest of the problem, cosecant squared beta. Just put in equals. Now look at what we have. What else can we do here? Well, I can collect like terms. These are like terms, and there's 2 of them. And lo and behold, we end up with exactly what's on the right-hand side of the equation. So your work is going to be the actual steps in getting down to, on this side of the equation, what you're looking for over here on this side of the equation. Or vice versa. You can work from right to left. It doesn't matter. All right, example 4. Okay, again, I see powers of 2. I'm thinking, I might use some of those Pythagorean identities. I'll work with the left-hand side. I want to get rid of sine squared z, and in my answer have a cosine squared z. I'm thinking a Pythagorean identity is going to help me with that. So I'll bring down the 3. It's not time to work on that term yet. Let's work on substituting something in for sine squared z. Well, if you look at your rearrangement of your Pythagorean identity of sine squared x plus cosine squared x equals 1, we can see that sine squared z would be equal to cosine squared z. No, sorry. It's because I'm not looking off of a formula sheet. Let me come over here. This is my Pythagorean identity. If I want to get rid of sine squared z, I'm going to move cosine squared x or z over to the other side. So it should be right here. I'm substituting in 1 minus cosine squared z. There we go. Equals, collecting my constant terms, 4 minus cosine squared z. And we're exactly where we need to be. So all of these check. Okay, for the last 2 examples, it says, look on page 490 to assist with verifying the following identities. I just put that there, but actually you can just use your formula sheet. On page 490, what you would be looking at is just a set of identities, but they're already present on your formula sheet. So I'm just going to put here, use formula sheet. All right, looking at number 5. I think the more complicated side of this equation is going to be the left side right here. Well, when I first look over here at my formula sheet, as you kind of scan down, I kind of see something similar that's in the problem. I see that I've got pi over 2 minus x here following a sine and cosine. I'm thinking I'm going to be working with the cofunction identities. A couple ways you can approach this problem. Okay, I'm going to look at the numerator and go, oh, cosine of quantity pi over 2 minus x. Well, cosine of pi over 2 minus x, or u in this case, is equivalent to sine of u. Well, in our problem, we have an x, so we're going to make this equal to sine of x. So the numerator here will get replaced with sine of x. Okay, find that cofunction identity, which is right here. It's equivalent to cosine of x in our situation. And then from here, I know that my target answer I'm looking for is tangent, but we do know that because of the quotient identity, that sine over cosine is equal to tangent. All right, what if we didn't enter into the problem that way? What if we took another approach? Some might do this instead. Some might go back to the original problem and they might look at cosine over sine, and that might be their focus. They might look at cosine over sine and go, well, when these two angles are the same in here, cosine over sine of the same two angles is going to go to cotangent of pi over 2 minus x. Remember, we're looking for tangent of x. But at that point, if they get to here, then we have a cofunction identity of cotangent of pi over 2 minus u equals tangent of u. So I'm just going to replace what I have on my paper here and change it to tangent and put the x down. So either approach doesn't matter. It's just whatever you see first. Okay, you might want to work with the numerator and denominator individually, changing those. Or you might see the bigger structure on the outside as this being cosine over sine being cotangent and work from that angle. Oops, doesn't matter. Okay, number 6, we're actually going to see two different approaches to verifying this identity. You might anytime pause the video, see if you can work the problem on your own. If you do that, I mean, self-assessing is better than just watching me do it. Do a little thinking on your own and then come back to the video. To me, the more complicated side of this equation is the left side. So notice that we have this big group of multiplication, or these factors right here, that's one term, and then after the subtraction sign, we have another term. When I first did this problem, my first thought was, well, let me multiply all of this together, and let me multiply all of this together. I'm not distributing secant to the 6th power inside to both of these because there's no plus inside here. Basically what this is if I take out the trig functions, it's the same thing as saying to somebody, take x to the 6th, multiply it by another x, if secant and secant are your x's, and then we have tangent of x, which we might want to think about that tangent function being a y. If you're asked to multiply all this together, your answer would be x to the 7th when you add the two exponents times y. So that's what I'm going to do here with the trig functions. I'm going to notice that secant to the 6th x times secant x with an understood exponent of 1 is going to give me secant to the 7x times the tangent that's still over here, considering that to be like a y. Same thing over here. There's no plus or minus in here for me to distribute, so it's just multiplying the trig functions and adding the exponents if we have the same trig function. So that'd be secant to the, how about the 5th power of x times tangent of x. All right, so I just multiplied together. Now I'm here, but I want to get to here. Well, the next thing I notice is that in these two terms here, I have a common factor. That common factor is that this term has secant to the 5th x power at least, like this one does, and a tangent x. And then this one, of course, has secant to the 5th x times tangent x. So in both these terms, I have at least 5 secant functions being multiplied. So let me take out the common factor of secant to the 5th x, comes out of here and here, and then both these terms has a tangent of x factor. Okay, now let's go back and divide out this factor from this term. Well, dividing out secant to the 5th x from secant to the 7th x leaves secant squared x, and then tangent x comes out from itself one time. So dividing this GCF out of this term leaves secant squared x. Don't forget, you can always multiply back in to check your factoring. Okay, what happens when I divide out this factor from this term? Well, notice this is identical, so I have -1. Again, check by multiplying these factors into each of these terms to get back to this previous step. Then I'm going to think about what I have inside here and think about Pythagorean identities. Go to your Pythagorean identities, the 1 plus tangent squared x equals secant squared x. Okay, look at your different rearrangements there. And this is actually equal to tangent squared x. So keeping the GCF, but now replacing this factor, that's a times, that's equivalent to tangent squared x. Okay, this is just one term. So secant to the 5th x, and when I multiply these two together, I'm going to get tangent cubed x, which was our target answer. Okay, so what did we do? Go back and revisit. We just multiplied together, kind of cleaned this up, then we refactored and made a Pythagorean identity substitution, and then cleaned it up again, resulting in our answer here. Again, like I mentioned, there's another way, another thought process about how to enter into this problem. So let me kind of erase the mess I made here. I want to again look at both of these terms here. Some might say, well, I don't want to multiply inside. I want to just get straight to factoring. So here's another approach in getting the same right-hand side of the equation. Let's just kind of study what we have here and what's the GCF. Let's get right to the factoring first. I noticed that this group right here has at least secant. Oh, I'm sorry. Let me rethink this. What did these two terms have in common? This is what I was thinking about. Well, they both have these factors. So what say you take out secant x times tangent of x? And I've got a parenthesis here. Coming back up here, when I take out this factor, secant x times tangent x, I'm left with secant to the 6th x minus, and then when I take out secant x tangent x, I'm left with secant to the 4th x. And then I can see that right here, I still have another factor. What happens if I pull out secant to the 4th x and put it up front along with these other factors? So that's what I'm going to do next. Take out secant to the 4th x, but I'm still going to have these factors. Okay, what happens when you take out secant to the 4th x here? You're going to have secant squared x minus, taking it out from itself as 1. And then here we can replace this with tangent squared x. So rewriting the GCF that's up front here, but replacing this with tangent squared x. Now all we have to do is kind of clean this up. This is just one term, one big group. And so I'm going to have secant to the 5th x times tangent cubed x. So are there going to be multiple ways to prove a trigonometric identity or verify? Absolutely. There's going to be several different ways. So, and they're all right, as long as you do everything right and you get the answer that you're looking for. All right, there you go.